have a look at practice question set number 16 that was due today. Starting with question number 1, it says a negatively charged particle is projected into a magnetic field as shown in the diagram below. We want to find out what the direction of the force on this particle is. So first we got to look at, I guess, the fact that it's a negatively charged particle traveling to the right. The velocity is to the right. The magnetic field is which way? We're not told this time. Usually we're told magnetic field is toward the right or to the left or upwards or downwards or whatever it is. Yeah? It's going which way relative to the page?
Downwards.
Yep. Yeah, good. It's going down the page because it's going from magnetic north to magnetic south. We know that magnetic field inside a magnet goes from south to north, but outside, of course, it goes from north to south. So we've got our left hand because it's a negatively charged particle, left thumb in the direction of the particle, which is to the right. Fingers are down the page from north to south. Palm's going to point out of the page. The magnetic force is out of the page. Now, we're not asked this about this question, but if we were, what would the shape of the path be? It gets deflected out of the page, but in what kind of shape?
It would be like a circle.
Yeah, it'd be a circle, exactly. Yeah, it'd be a circle. Charged particle in an electric field, perpendicular to an electric field, that is, will go in a parabola, but a charged particle perpendicular to a magnetic field will go in a circle. All right. Good. Number 2, charged particles moving toward the Earth are trapped within a field near the Earth where they cause the aurora borealis, which are the northern lights, and the aurora australis, which are the southern lights. The field in which the particles are trapped is the, it's not going to be the electric field that doesn't exist around the Earth. It's not going to be the, what? The induction field? So which is it going to be? The gravitational field or the magnetic field? Yeah, it's going to be C. They don't get trapped in the gravitational field. The gravitational field points directly toward the Earth. Now, it's not going to affect these particles dramatically because these particles are so light. But even if we do look at the minuscule effect of gravity on these tiny little particles, all it's going to do is cause them to speed up. It's not going to cause them to be deflected or to become trapped in that field. So it's got to be the magnetic field that surrounds the Earth that causes that. Numeric response question number 1, my favorite one on here. In fact, as I was looking at it earlier this morning, I was thinking, man, I wish I had saved this for your unit test on Thursday. Such a great question. A positively charged ion, I'm going to circle that right away because I'll probably use my left hand if I don't. A positively charged ion travels through a region that contains perpendicular electric and magnetic fields. The ions pass through the region undeflected at a constant speed. What does that word tell us right now, undeflected? It is something that leads me to, and it should lead me to every time I see it.
The electric force is equal to the magnetic force.
Good. Two forces have to balance each other out. Remember this, fields will never balance. Fields will never balance. Forces can balance. So you got two fields here, electric and magnetic. That's great. They won't balance. But if a particle goes undeflected through the two, then the electric force must balance the magnetic force. Got it? So in other words, one force has got to be up and one force has got to be downward. Let's look and see what we can figure out here before we even read the question here. We've got a negatively charged plate and a positively charged plate. That means the electric field points upwards toward the negatively charged plate. And that would mean since we have a positively charged particle, the electric force would also be upwards. Right? The electric force on a charged particle, a positively charged particle, is in the same direction as the electric field. That's the last unit, right? But we know that we're going to see that again on Thursday's test, stuff from last unit. All right, let's look at what the question says here and see what else we can do. The direction of the electric force is upwards, so that's going to be option 5. The electric field is also upwards, so that's going to be option 5 as well. What about the magnetic force? We don't really have much information about the magnetic effect here, right? If the electric force is upwards, then the magnetic force has to be, Kayla? Downwards, yeah. because it has to be equal and opposite. So we're going to say that that one's going to be option 6. What about the direction of the magnetic field? This is a hand rule for deflection one now, right? Thumb in the direction of the particle, right thumb in the direction of the particle, which is towards the right side of the page. Fingers in the direction, sorry, palm points in the direction of the force, which is down toward the bottom of the page. My fingers stretched out will automatically point out of the page, which is option 0. So 5560 is our answer there. That make sense? Thumb in the direction of the particle, palm points down the page, because usually it's thumb, fingers, which way does my palm point? This time it's thumb, palm, see which way my fingers point, right?
Why are they different?
Why is what different?
Well, how do you know any of these?
Well, we know this is a hand rule for deflection problem, firstly, because we've got a force. Okay, when you're dealing with a magnetic force, you're going to use the hand rule for deflection. So now it's just a matter of, do I do thumb, fingers, palm, or do I do thumb, palm, fingers? We got to know what's what. Thumb is the direction of motion of the particle. I know that. Fingers are field. I don't know that. Palm is force. I know that is downwards, right? So usually I have thumb. I know the direction of the particle and the field. I want to see which way the force is. This time it's just kind of rearranging, right? I know which way the particle is moving. I know which way the force is. Okay. I want to see which way the field is, which way my fingers point. Force is palm. Field is fingers. Yeah. So 5560 is our answer there. 3. In a magnetic field of strength 5.6 times 10 negative 2, an alpha particle travels in a circular path. I'm going to circle that because it's positive, although I don't think it's really going to matter too much for this one. What's the speed of the alpha particle? So we're going to say for this one, well, we know that Fm is equal to QVB applies here. So does Fc equal to mv squared over r apply. But remember what we said in these particles, or sorry, in these questions where you've got a radius, odds are you're going to use the combination of the two. Fc equals Fm. So we'll say mv squared over r equals qvb. One of the v's cancels. Solving for b, the speed of the particle, the r goes up, and then the m goes down. Becomes qbr over m. Now we sub our numbers in. Make sure you make the charge of the alpha particle 3.2 times 10 to the minus 19. And then, of course, the mass is 6.65 times 10 to the minus 27. When I do that, I get 1.72 times 10 to the 4 meters per second. Now, when you click on check your answers, when you submitted this, you saw that the answer is 12724. That was actually incorrect. Okay, the answer should be what? 1.72, because this is a b times 10 to the w question. If it was a decimal b c times 10 to the d, then 1724 would be correct. B times 10 to the w, it's just 1.72. Good? And the next question, I think, is the last one. An electric field strength of 1.5 times 10 to the 4, perpendicular to magnetic field, so 3 times 10 to the negative 3. Electron moves perpendicular, undeflected. There we go again, right? Undeflected. Two fields have to balance. No, two fields never balance. Two forces need to balance. Good. In this case, it's going to be the electric force and the magnetic force. So we're going to say Q times E is equal to QVB. Q's cancel. V is equal to E over B. And when I do that, I end up getting 5.0 times 10 to the 6 meters per second. If I had to predict, if I had to guess what the answer was, I would have guessed that one. What do we usually say the speed of charged particles is? Not always, but usually. 10 to the 5, 10 to the 6. Could be 10 to the 7. Almost certainly not going to be 10 to the minus 7. Right? Those are almost certainly wrong. So when we solve this, we're just confirming what we thought would have been the case anyways. Pretty sure we're right because the number falls right in that range.